You can keep your bag on here.
You have many exams.
You have then we can just directly put it onto the. Oh yes, yes, that's perfect. We have a small notation.
Okay, no problem. Times have changed.
I'm trying.
Recollect is it which
What is it? What?
so there is
The hat.
अभिषेक सर को लिंक भेज दिया हाँ भेज दी
The same classroom.
Exams also be here in this classroom. So typically some lab Michael used to be here.
Yes.
We used to sit here, very scared because what will be the questions? Because my roll was roll number 2. And first my used to come, and then after I reached, everyone used to gather around me. What are they asking? What is the questions?
পরীক্ষা চলছে বন্ধ করতে বলো না তার ছেড়ে দেবো না
বন্ধ করতে পরীক্ষা চলছে Last week I met Ashish Verma and Saurabh over phone, over video call.
That day they called you also. They were calling everyone. We also they called.
In the month of December, last December, Ashish came. And till date I am having a very close relationship as well. हाँ तो बोलते you are from गया, हाँ तू तो गया बेटा.
Both of you are in the same passion also. Yes. In terms of your other passions.
Last year I underwent 4 surgeries. Back to back. Half of my right lungs is gone. 3 leaves are gone. And I took near about 7 to 8 months of leave from that. Now gradually I am recovering. That Maximus no longer there. That is there to manage the lungs volume. That has been granted inside the lungs. That's the way. And now recuperating. And I have joined again.
That's good, sir. Because that is a motivation for me also. I
If
see
you lift weights, weight will lift you.
you. the same age like that.
At the age of near about 50, if I'm not having any comorbidities, that is enough for me. That is the definition of fitness.
So start, sir.
Hello.
अच्छा
Hello. Hello. अच्छा. So today is the fifth day of this auto training and learning academy sponsored program, FDP program on application developments in the lab on cheap technology for fluid and thermal sciences. So we are having with us our most beloved student and Dr. Siddharth Tamang, who is an alumni of this institute, 2012 mechanical engineering pass out, and Dr. Venkata Naga Vamsi Munagala is there. We are having with us the Dean of School of Engineering, Professor Dr. Turun Kantijana. We are having with us the Head of the Department of Mechanical Engineering, Dr. Gautam Kumar Ghosh. We are having with us Professor Devabrata Ghosh, who is the Associate Professor in the Department of Applied Electronics and Instrumentation Engineering, and who is simultaneously taking the charge of Industry Institute Partnerships. Participants, colleagues, students, it is a matter of great elation when you see a student of your own institute has unfurled his credential and serving an institute of national, I must say international importance, IIT Kharagpur, and he has come to the alma mater to enlighten us and to complete the cycle. The loop is complete. So Dr. Siddharth Tamang is there, and I was his BTech, project supervisor, and I used to take regularly his classes. And today I listen to him in the same class, the same podium, the same benches, but just the reverse engineering. Okay. Once it flowed from my end to him, now it will flow from his end to my end. So I congratulate you as you have come to your alma mater, and you have taken so much of pain in spite of your busy schedule. You have come here to enlighten us with your academic credential. So I must welcome you for that. Next, Dr. Venkata Naga Vamsi. Sir is also.
Don't call me sir, call me Vamsi. Very feel free to call me by my
Service Mahoday.
name.
Dr. Venkata Naga Vamsi is he has also taken lot of pain to come to our place, and what to say, I'm feeling a bit enlightened to see my student and his fellow friend at this place, and after so long time I'm seeing you for after 12 years. So let me unfurl the brief bio sketch of both the speakers. At first, Dr. Siddharth Tamang, who is presently working as Assistant Professor of Mechanical Engineering Department at Indian Institute of Technology, Kharagpur. He completed his BTech in Mechanical Engineering from Haldia Institute of Technology in the year 2012 and went to pursue MTech degree in Mechanical Engineering from ISM Dhanbad, IIT ISM Dhanbad. He completed his PhD from Department of Mechanical Engineering, Indian Institute of Technology, IIT Delhi. He has also served as Research Associate at Foundation for Innovation and Technology Transfer, FITT, IIT Delhi. where he addressed issues faced by automobile industry in gear manufacturing. He is also the recipient of IRD Early Top Fellowship from Industrial Research and Development Unit, IIT Delhi, before joining IIT Kharagpur. Before joining IIT Kharagpur, he worked as a temporary faculty in Mechanical Engineering Department at IIST Shibpur, formerly Vishu, West Bengal. His research is in the area of metallic additive manufacturing and joining of dissimilar materials. His other research interests are processing of materials, ceramics and composites by microwave energy. His study focuses on manufacturing process development, mechanical property enhancement, and material characterization with the help of experimental study and finite element analysis. He enjoys traveling, cinematography, photography, hiking, and playing table tennis. And he used to, at his time, he represented our college for national level, state level, pertaining to table tennis. So this is the brief bio sketch of Dr. Siddharth Tama. And now, Dr. Ramsi obtained his bachelor degree in mechanical engineering from Osmania University, Hyderabad, in the year 2013. After completion of his bachelor degree, he joined IIT Madras to pursue his masters in metallurgical and materials engineering. Later on, he joined McGill University, Canada, to pursue his PhD on metal matrix composite coating and the tribological aspect of different operating conditions. And for his research, PhD research, he got, he was awarded the prestigious bronze medal and Department Research Excellence Award for his PhD. After completion of his PhD, he worked as the postdoctoral fellow at McGill University for 2 years on a project jointly funded by QRIAQ and Pratt and Whitney. And in May 2022, he joined the Department of Mechanical Engineering, IIT Kharagpur, as assistant professor. And at IIT KGP, his research group focuses on development of novel coating technologies to improve the performance of life of engineering components operating in different environments. He has published a number of peer-reviewed journals of international review, and his research interest mainly focuses on surface engineering, coating fabrication, and tribology. And he also loved to play cricket and trekking and watching movies. So these are the bio sketch of the two speakers of today. Now, before we start our technical session, we'd like to felicitate our honorable speakers with Uttari. I will ask Aisha, a fourth year mechanical engineering student, to do the honor on behalf of the department. Now I will ask Dr. Gautam Kumar Ghosh, the head of mechanical engineering, to give away the potted plants to the students. I will ask Professor Devadatta to hand over the plaques on behalf of the department. Plaques. I'd like to request Professor Dr. Turukanti Jana to hand over a memento and a diary on behalf of the college.
Thank you so much, sir. It's my pleasure. So many mixed emotions coming out.
Follow
Now the inaugural ceremony is over. Now I'll ask Dr. Gautam Kumar Ghosh to say a few words.
Okay, good morning everybody. Today we are having the valedictory session in the second half. Okay, 2:30 onwards. Persons from industry will be visiting our place, so attendance is compulsory in this session. Okay, since we are having an FDP, so the valedictory session is compulsory for all the participants. So please be present from 2:30 onwards. Okay, so it will be a very short valedictory session. So I hope you will be present at that session. Okay, it's compulsory for all the participants. Thank you.
Now we can move forward directly the technical session.
Videos I can take
No, it will be there, but it is already in the presentation, so it won't be different paper.
Which one?
Cancel.
So, good morning everyone, and firstly I would like to thank the speakers who have spoken before me for the kind introduction. It feels that as if I came back to my own college, because I also was from a private engineering college when I did my BTech back in 2013 in Hyderabad, so it was very nice to be back always and to get some memories back. So today basically I'm slightly away from the theme of the program, so I thought like better to give some insights on the thermal spray coatings, which is nowadays picking up a lot of popularity in case of automobile and aerospace applications. So I'll just go through briefly the different thermal spray process, and then I'll go into a novel thermal spray process, which is a cold spray, okay, which started in 1990, and now in North America and all over the world it is picking up due to its unique characteristics. And I'll show you a few results from my PhD, and of course we can have a discussion at the end. So just a brief background about myself. I did my bachelor's from Usman University, Hyderabad from 2009 to 13, and then I moved to IIT Madras to do my master's. So in my master's I was basically working on the electrodeposition of nickel tungsten and nickel based nano composite coatings, typically nickel tungsten silicon carbide nano composite for wear resistant applications. And then when I was at McGill, I changed the track a little bit, and I started to work on much thicker coatings, which is basically using thermal spray process to deposit metal matrix composite coatings for tribological applications, both for room temperature and also higher elevated temperatures. And then after I graduated with a PhD, I continued at McGill. I was a joint project with McGill Concordia and Consortium of Aerospace Innovation Quebec, and and with Pratt and Whitney we started to develop some coatings, multi-material coatings for aero engine applications, where there was fretting and where that was occurring in this in this engine components. And there we were looking for some thermal spray coatings also, and also we were depositing from some self-lubricating nano composite coatings for Ford, the automobile company. And later on, after 2 years, I joined basically IIT Madras, IIT Kharagpur, and there now I am trying to establish a research group to develop novel coating technologies for high temperature tribological applications, typically solid lubrication at elevated temperatures, and also some electroplating, which is one of my expertise. So this is a brief bio sketch. And today whatever I am going to talk, mostly the results will be from my PhD thesis, because at IIT KGP we are still working in progress. So just background of surface engineering research group at IIT KGP, two professors, I am there and Professor Bandyopadhyay is there. I am closely working with him. So he is pretty experienced, almost 13 years of experience he has gathered in field of thermal spraying, and he has also guided around 13 PhDs. Okay, I am jointly guiding one PhD scholar with him. So we are closely working. So our research group, that is Surface Engineering and Tribology Research Group, we have projects right now sponsored from DRDO, ISRO, and some from Pratt & Whitney, Canada, and all, which we have already finished. So the coating fabrication facilities what we have at IIT Kharagpur in-house, basically we have plasma spraying, which is one of the thermal spray process. We have some Acura spray through which you can do particle temperature and velocity measurements, and to test these coatings we basically have a high temperature tribometer which can do room temperature and elevated temperature tribometer, that is wear test, which can go almost up to 800 to 1000 degrees centigrade. And of course we have scratch tester to check the adhesion strength and cohesion strength of the. So publications, we came engineering, they are welcome to apply for the upcoming semester. Typically we have 3 PhD positions right now. So that completes my some basic introduction. So just like to move on into the technical aspect of my talk. So today I will be giving you about a brief introduction why we are so much concerned about friction and wear in different industries, and then I'll move to a basic introduction about different thermal spray processes that are typically there in the field, and then cold spray process, which is a novel thermal spray technology which is evolving with time, and how cold spray can be used to deposit some of the high performance alloys like titanium alloy, titanium 64, etc., and how we can fabricate metal matrix composites, and then their tribology, and I'll move towards the conclusions. So why friction and wear? First, if we look at the world energy consumption map, we see that the energy consumption, the requirement for, I think the pointer is getting trouble, but anyways, the friction and wear, if you look at the growing day by day. Okay, and if you look at the statistics by US Energy Department, we see that still much of our energy is coming from fossils. Okay, although we are moving towards renewable energy, but still a major chunk of our energy requirement is still met by for burning of fossil fuels. And now if you look at how this energy basically which is produced and how much is wasted in friction and wear, basically you see that 1/3 of the energy whatever you are consuming, lot of energy is going into friction and wear. Okay, and when you sum up all the energies basically that are wasted in friction and wear, you see that the summation of the energies wasted due to friction and wear is more than the energy consumed by the second highest country. So lot of energy is going into wastage due to friction and wear. So if we can mitigate the friction and the energy loss due to friction and wear, that is loss of energy, the energy consumption will come down, so that we will move towards greener economy. Okay, the dependence on fossil fuels will also slowly start coming down. So that's why people are very much concerned about producing or fabricating coatings that can actually reduce friction and wear. And if you want to look at in terms of numbers, if you look at just the aerospace sector, around 10% of energy is lost in friction, and they spend near about 105 billion Canadian dollars every year to basically overhaul, remove the parts, replace the parts which are getting worn out typically due to friction and wear. Okay, and that accounts for 40% of the engine parts. Okay, after particular cycles, they have to be removed because there is wear damage that occurs into these parts. So lot of money is getting wasted there, and also the energy consumption. So if we can try to come up with coatings or the processes through which we can reduce this friction and wear, we save a lot of energy, and the energy requirement will come down, and as a result, you will burn less fossils. Okay, and then you will start going to a much greener economy. We see that the temperature, the climate change, all these things are coming more and more into picture. So one of the ways to fabricate coatings which are resistant to wear and also can lower the coefficient of friction is through thermal spraying. Okay, thermal spraying is an attractive technique. It's a very old technique where basically you take the material you want to coat in the form of powder, rods, etc. You melt the feedstock particles, okay, using different type of flames, and then you accelerate this molten particle to impact onto a substrate, allow it to solidify and form a deposit. Okay, so basically you melt the initial feedstock, you accelerate it, propel it, let it impact on the substrate, and then you basically form a deposit. Okay, so you see that we see that the powder particles are coming in the figure which is there basically in the left hand side bottom, where you basically have powder particles that are coming up and they are deforming, or melted particles are solidifying, and then you actually start building up a coating. Here the powder particle size which are looking are typically about tens of microns, that is 40 microns, 50 microns. So you start at a powder particle level and then you slowly bring up the particles. So this is how a coating looks like. If you cut the coating and put it in an SCM, we see that you have the coatings. The small particles are the small particles which have carried out the base, and that is your base metal and substrate. So any thermal spray process, the basic philosophy remains the same. Okay? Basically, except the cold spray, which is slightly novel, you will see. So you melt the particle, you accelerate, and then impact, and then you form a deposit. So here are the powder particles. If you individually see, those are the particles that are getting deposited. Okay? This is a solid state deposition. The particle has basically deformed, whereas down the particle has melted, and the molten metal particle is basically put on the substrate. So that's why you see a more jetting action behavior. And if you cross section the powder particles, you can actually see what is the microstructure of the powder and how the microstructure in individual particles contribute to the mechanical properties of the bulk coating behavior. So it is a different length scales. Basically you can tune your process by changing the microstructure, the mechanical properties of the powder particles, and you can also tailor the bulk properties of the coating. So it is a different length scale, starting from micron size scale to the bigger length scales, that is millimeter, where you start depositing. And using thermal spray processes, you can deposit coatings starting from tens of microns to millimeters. So very thick coatings can also be deposited. So that is one of the advantages of thermal spraying processes. So if you look at thermal spray process broadly, depending upon how the flame, that is the heat source, you have conversion where you have flame spray process. You are using a flame to basically melt your powder particles. You have high velocity oxy-fuel spray. We have high velocity air fuel spray, and we have detonation gun spray. And if you are using an electric arc, basically you have wire arc spraying, you have plasma, and kinetic energy cold spray. We'll just briefly look at all these processes and go into cold spray because it's a novel thermal spray process which has come up recently. So flame spray, it's a old process, near about 1900s it was invented. It's the first process. It's a simple process where basically you have a fuel oxygen mixture that is ignited, and the feedstock, that is the powder, is taken either in the form of powder or a rod. Okay, it's melted, okay, and you have a gas that flows, okay, the accelerating, the propelling gas, and that accelerates, and you deposit the powders basically on any of the substrates. So here the fuel typically is kerosene, because back then when they invented, they started using kerosene. So now oxyacetylene, those things also have come into picture. The advantages: low cost. Okay, the cost of equipment is not that much. This is typically a workshop type process, and you have simple in design. The gun design is not very complicated. Still very good process to be being used. Generally, it's used for depositing coatings for corrosion protection, okay, where it is not mechanically impacted by different external forces. The coating doesn't fail. Here you have corrosion. The corrosion protection, zinc coatings, etc., low melting point materials are basically deposited. one limitation of this process is the porosity is very high. Okay, the coating will not be very extremely dense because you are not completely melting the particles. The velocity of impact is less. So basically, you can have some kind of lower, higher porosity, that is around 10 to 20%, and low adhesion and cohesion strength. Little bit, you might have some problems. Started to pick up. Okay, so oxyacetylene flames, welding also picked up. So that's why they started using oxygen and fuel typically. Here also sometimes they use kerosene and or acetylene also. So the oxy-fuel mixture is basically fed in. Okay, the powder is fed, it is combusted. Okay, and in the combustion, and after that the gases are released, they are expanded basically through a convergent divergent nozzle. Okay, earlier it was mostly a convergent nozzle, but here is mostly convergent divergent nozzle, so you get much more acceleration and velocities. So impact is at a higher rate. Okay, so as a result, your adhesion is more. Okay, the coating quality actually improved. Okay, so and the temperatures also improved because you're using acetylene as one of the fuel. So they started to coat ceramides. Okay, that is metal matrix compounds, tungsten carbide cobalt, one of the very popular coating which they use for rolling mills. So you see the rolling mills, paper mills, the rolls on which the paper actually goes, they are basically subjected to wear and tear. So tungsten carbide cobalt coatings are being deposited on that, and HVF is one of the very flagship process that people use. So high wear resistant coatings, thick coatings, okay, you can have high deposition rate, and low heat input to the component. You can change the distance between the gun and the substrate, okay, so that you can see there is minimal heat transfer to the substrate. Limitations: brittle coating and chances of oxidation are more. Okay, because you are sending oxy-fuel mixture. So if your material is very sensitive to oxygen, okay, if it will oxidize like aluminum, etc. So alumina formation will occur. So if that is not desired, then in that case this process is not very suitable. Okay, that is one limitation of this process. But the advantage is you can coat metal matrix composites directly. So now the oxidation problem was troubling people. So now what they did, they wanted to reduce the oxidation issue. So now they started sending air and fuel mixture. Earlier it was oxy and fuel. So the temperatures of the particle which is getting melted in the combustion zone is higher. Now they started sending air fuel mixture. So the temperature slightly came down because you have nitrogen also in air. So the air fuel mixture is being sent. So as a result, the oxidation problem also came down. Okay, so some materials which are oxidation sensitive, if they are cannot coat with HVF, which is a derivative of HVF, started to pick up. Next is detonation gun spray coating. Okay, this typically is very rarely used. It is something like HVF only, but the main difference is here basically you are giving the air fuel mixture in a pulse. Okay, there it is a continuous combustion, the gas is flowing, the coating is deposited. Here basically you are giving in a pulse. So basically you are giving air fuel mixture and then you are igniting it with a spark and giving a pulse. So the pressure wave basically carry forwards your coating that is deposited. Here you can have straight barrel or sometimes also a convergent barrel is given to get some higher velocities. And between the pulses of air fuel mixture, sometimes nitrogen is also purged to give some kind of reducing atmosphere so that you don't oxidize your powders too much. So because since you are melting your powders, there is very high chance of it picks up oxygen. Okay, so that's why they give pulses of nitrogen. So not very common process, but still in some places we use. HVF is more common, one of the most common processes. So people also use wire arc spray. So in that there are some materials where maybe making powders is not very feasible. So there they make it as wires and rods if it is available, and they connect them to a DC power source, and one is given positive polarity and one is given negative polarity, and they are being touched and arc is generated, and within the arc the rod or powder melts, and there is a propellant gas which is given from bottom, which is accelerated and it hits and basically forms a coating. The advantage here is basically like previous process, you have a hot gas stream that is hitting your substrate, and suppose your substrate is temperature sensitive, that is with like something like polymeric substrate, which is very yes sir. Yes. Okay. So yeah, if your substrate is temperature sensitive, okay, so in this case, basically this is helpful because you don't have a hot gas stream that is hitting basically. Okay. So some temperature sensitive material can be coated using wire arc spray. But the limitation here is basically your wires should be electrically conductive. That is one particular limitation. Otherwise, you will not have the conductivity and arc generation will not be problem. So next is plasma spraying. So why plasma spraying has come into picture is basically people wanted to start to coat ceramics. Okay. So till now whatever they were coating was mostly metals and metal matrix composites. But people wanted to coat high strength materials, okay, high hardness materials, ceramics. So if you want to coat ceramics, this is only one of the popular method, that is plasma spraying. Because ceramics, we know that the melting point is very high. You need a very high temperature to melt these particles, and that temperature is achieved basically by using a plasma plume. And powder particles are inserted in the plasma plume from the top, okay, and there is a gas that accelerates, and then the molten ceramic particle impacts. So all your turbine blades of aero engines, which are coated with different thermal barrier coatings, zirconia, yttria stabilized zirconia, these are coated using plasma spraying process. Okay. So the ability of plasma to generate very high temperatures in the zone where the powder is fed makes this process one of the most attractive process till today to coat ceramics. So if you want to coat ceramics, this is, I would say, the only process in thermal spraying which can actually deposit ceramics. Okay. So last is cold spray. So what happened eventually is basically in 1990s in Russia, people started to think that for repair application, the concept of sustainability started to pick up. Till now, replacing components. Now they started to say, can we reuse the component? Can we repair? Because if you have a weak component, a particular section has gone worn out, you don't want the entire component to be replaced. It is a very issue because market is growing and you don't want. So is there a way where we can locally repair the component and try to reuse maybe for 5 more years or 7 more years? So that's when this cold spraying started to pick up. The advantages of cold spray started to pick up. In cold spray process, what happens is, we will see much more in detail in the coming slides. Powder particles are accelerated. They are not heated but accelerated to supersonic velocities, 600 to 1200 meters per second. And cold spray is used only for ductile materials, which are plastically deformable. So they impact, plastically deform and form a deposit. You can imagine like a clay. You throw clay at some normal velocity, it sticks and maybe it falls. But if you increase your velocity to a certain critical point, which you throw at such a velocity, it just sticks there. Okay. So that philosophy has come into basically cold spray. So since you are not melting the particle but just accelerating it to higher velocities, the bulk properties of the material are preserved. Because if you heat, you will have some phase transformations. Oxygen pickup might be there because of the affinity to oxygen. But if you are putting at room temperatures only, but using the plastic deformation property of the material, then you are inhibiting any phase transformations. For example, if you are putting copper using plasma or any other spray process, copper oxide formation will occur. And if you are looking for application for electrical conductivity, presence of this oxide in the coating itself will reduce your conductivity. And suppose you want to repair a copper component at a particular location and you have used some thermal spray process, your conductivity will be affected. So the bulk property of the material is not preserved. But if you use cold spray where you don't have any oxidation, you will get native material property. So that's when cold spray is very useful. That is, no phase change, negligible oxidation because you are not melting or doing anything. Okay. So only thing is, problem is expensive little bit. The equipment is slightly expensive. Right now the research is going on. Metals and metal matrix composites are being deposited using cold spray. So yeah, this is the concept of critical velocity that I was discussing. So initially if you throw it lower velocities, it will not deform, it will just rebound. But if you cross a critical point, similar to what clay example I throw at higher velocities, it will stick and stay. So that is the concept of critical velocity, where the deposition actually starts. And it depends on many physical and chemical properties of the material, like material density, what is its yield strength, okay, how ductile it is. So one criteria in cold spray is you can only coat materials which are ductile. If you want to coat brittle materials, you should have a ductile matrix so that the ductile matrix will default and the brittle materials actually get embedded inside. Something like cake and cherry model. If you have a cake, your cherries are hard particles which are embedded inside it. So that's how is the cold spray process. So this is the bonding mechanism as I have discussed. So particle impacts, okay, and you have the plastic deformation that occurs at the very negligible region, and that is the jetting action, and the particle actually bonds to the body. Okay, so the bulk of the particle temperature is at a very low state, whereas only at the interface, due to the impact, temperature will be high, but since there is a bulk substrate, the heat dissipation is faster, so the bulk of the material stays at very low temperature. Cold spray is not like it is below room temperature, it is only the thing, the melting point of the particle, the temperature of the particle is much lower than melting point. That's why they have termed it as cold spray process. So last, there is a salient thermal spray process. You can see that your plasma temperature is very high, so that's why you are using ceramics. Other process, lower temperatures, cold spray very high velocity and low temperature, only 300 degrees, 100 degrees centigrade you can see. So that's why you are using it as one of the popular processes. So thermal spray coatings, lot of applications. So you can see in aero engine turbine blades for wear resistant applications, biomedical impact plants, titanium coatings there. Repair of one components. You have one component, you repaired it, you machined it, and you can reuse it. And tungsten carbide cobalt coatings for paper mill applications, antibacterial, COVID times. Okay, we all remember COVID times, so antibacterial coatings on frequently touched surfaces like door handles, okay, beds of hospitals where it is frequently touched and you don't want bacterial infections to grow. So there the copper coatings come into picture. Okay? This go back to our age old where we used to drink water in copper vessels and all, the same phenomenon. So now I'll go back into my research for next 10-15 minutes and I'll try to wind up. So cold spray of titanium and titanium based composites. So if you can see the graph, the other coating process, the plasma spray etc. are higher temperatures, whereas cold spray is low temperature and high velocity process. So that's why it is typically used for repair of worn components because you are preserving the bulk property of the material. It is also used to additively fabricate free-form parts. If you have a small free-form parts which you can additively want to manufacture, you can actually fabricate using cold spray. And coatings on heat-sensitive materials. So you don't have gas that is going at very combustion gas that is going and heating. So you have a substrate which is heat-sensitive, like plastics. If you want to coat metal on a plastic, this is one particular process. And here you can see zinc coating is done on a glass substrate. Okay, so metal coating is being done on a glass substrate which is heat sensitive. Okay, somewhat. So that can be done. So applications, why this process now is picking up, you can see a B-1 bomber aircraft of US. So it's there's a panel of aluminum alloy. So typically you have to remove the panel, sometimes do some inner engineering, something has worn out, and then fix the panel again. Again you remove a panel. So what happens is, every time they remove this riveted joint, they started having wear on that joint, and replacing this panel is very expensive. So what they did, they used cold spray. Basically, since you are protecting the native property of the material, they sprayed aluminum alloy, whatever is the material, they machined it, and it is again good to go to use. Okay, so the repair applications start coming into picture. Electronic industry, you basically need conductivity on non-conducting substrates. Okay, suppose you have heat sinks, okay, or plastics on which you need some conductivity. So you want to deposit a copper layer on top. So cold spray is one attractive process, because you basically have heat resistant substrate, that is the plastic or the printed circuit boards, your PCBs, and on that you can get conductivity. Aerospace, NASA is doing lot of additively manufacturing nickel and titanium combination of materials and depositing. Okay, so they have some super alloy that they have deposited for thrust chamber of rockets. And last is basically aesthetic applications also, copper coatings on glass substrates. Okay, this is one of the. So the applications are too many, that's why cold spray is getting researched a lot nowadays. So coming to titanium alloys, we all know that the high strength to weight ratio makes titanium one of the most attractive material, but it has some difficulties in terms of machinability and getting titanium, from ore always becomes difficult, and it is very costly affair to purify titanium and all because it gets oxidized. So in that case, cold spray can be used to additively fabricate the titanium parts. Or if you have already a titanium part, you just want to repair it, you don't want to replace it. In that case, cold spray will be very useful. But there are some challenges in cold spray. If you look at the powders which you use for titanium and titanium alloys, because the powders are manufactured using gas atomization process where you have rapid heating and then you cool it immediately to get the spheroidized powders, and titanium has a phase transformation at 890 degrees centigrade from BCC to HCP, and since it's a fast cooling, you will have martensitic microstructure which is very hard, and when you cold spray it, since it is hard, it is difficult to deform. So as a result, you will get, when you are using nitrogen as propellant gas, that is to accelerate the particles, you end up getting very porous coatings. On the other hand, when you use helium, which is a monoatomic gas, and for the higher expansion ratio, you typically accelerate particles to very high velocities and typically get very dense microstructures. But the problem with helium is, it is very expensive, almost 20 to 30 times than nitrogen. So it is unsustainable. So if there is a way through which we can use nitrogen and also get dense coatings, then it is very good for us because it becomes sustainable and it also helps us to basically repair the components. And also the wear of titanium. Titanium components undergo extensive wear because of the non-protective nature of surface oxides. Okay, so we have two challenges. That is, one, to improve the tribological properties of titanium, and also to see a way through which we can get very dense deposits, because porosity in coatings is a problem. Okay, especially then you have secondary mechanisms that come into picture, that is fatigue, crack, and coating delamination. So what we did basically is we tailored the microstructure of the powders. So we had traditional spherical powders which we fabricated using plasma gas atomization process, and we could see some martensite lathes. We adopted a different process which is known as Armstrong process. It's a modified cross process where there is no rapid heating and basically cooling. Basically it's a chemical reduction process, and then we could see that when you use chemical reduction process, one, you can basically get irregular morphology of the powders, and when you look at the microstructure, that is you cross section the powders and look at SEM, you see it's a more equiaxed microstructure, that is grain like microstructure. So martensite is hard to deform, whereas grain like structures is easier to deform, and then you are getting the irregular morphology also. So we tailored two properties, that is the morphology and basically the microstructure also of the powders, and we cold sprayed it using nitrogen as propellant gas, and while we are spraying we tried to measure the particle velocity also using a particle velocity monitoring system. We found that the spherical powder particles were accelerated to an average velocity basically of 619 meters per second. For the same input spray parameters, the irregular powders, okay, due to the irregular morphology and higher drag force in the free gas stream, they were accelerated to basically 732 meters per second. So by changing the morphology for the same input parameters, you are getting actually higher velocities because of the change in morphology of the particles. And secondly, when we looked at the microstructure, the spherical powders, we knew that will have high amount of porosity, that is around 13%, and we could see undeformed particles. Whereas when we used irregular powders, okay, since the microstructure of the powders were highly deformable, we could see that we had extremely dense microstructure with porosity less than 1%. So by tailoring your powder properties, you can actually reduce the porosity, okay, and also get very high dense microstructure. So by changing the powder properties, we could address one of the issue of reducing the porosity. So next, we wanted to address the next challenge, that is to improve the wear resistance of the coatings. So for this, what we did basically is we actually mixed the spherical and irregular titanium powder particles with titanium carbide. Okay, so we fabricated a metal matrix composite. So it is like a softer matrix with hard particles inside. Why we cannot put only titanium carbide? Because it's a brittle material, it's a ceramic, when it impacts it will break. So it will not plastically deform. But when you have a titanium matrix, these particles will deform and the titanium carbide particles will be embedded inside it. Okay. So that philosophy we used, we co-sprayed them. This was titanium 64. You can see we could fabricate a metal matrix composite where we had basically the round particles which are embedded in fragments which are embedded inside the coating. So it is like a cake It's a softer matrix but hard particles inside. And we could see that some particles had actually broken, okay, and some particles we could still retain their morphology, because when it impacts, some particles hit it and they try to break because of their brittle nature. It's evident in case of brittle materials, but we could retain near about 23% of maximum carbide particles inside our matrix. So once we did it, we actually did wear tests. Okay, that's standard trigonometry test where we had a ball that slides and then determine how much material is being lost. So we had two objectives here. Basically, one, to see how this second particle reinforcement, that is titanium carbide particle reinforcement, will improve the tribology of the materials, and second, basically how the microstructure below the wear track actually deforms. So we looked at first the coefficient of friction, which was monitored during the entire test. You see that in case of titanium 64, the friction is highly fluctuating, and the average friction is around 0.6. Okay, if we average the black hole. Whereas in case of composite coating, that is the titanium carbide, initially it was same, but after a few cycles it falls down and comes an average of 0.3 or 0.33 depending upon the titanium carbide. So you see that reinforcement of carbide particles had actually decreased the friction. That is one observation. Even at higher loads, we change the load, we could see that there is a drop in friction in case of composite coatings with higher titanium carbide composition. We will see why this happens. So after the wear test, we basically measured the wear volume and we calculated the wear rate. So we observed that compared to titanium 64, composite coating showed 1/10 less volume material removal rates. Okay? And even at higher loads, we could see the carbide coatings with highest volume fraction, the wear rate is actually very less. Okay? So to see why this phenomena is occurring, we looked at the wear tracks. Okay? So the wear track of titanium 64, we could see abrasive flowing. Okay? So the oxide has formed, it has broken down, and it is actually grooving the material, and that is resulting in highly fluctuating coefficient of frictions and basically the high wear rates. And these particles are mostly oxide particles. Whereas in case of composite coatings, we saw that the protective tribo layers are being formed around the carbide particles. Because carbide particle is there, the wear debris come, okay, between the ball which is under load and the carbide particle is hard. So there is basically sintering action that is taking place around these carbide particles due to high load and localized temperature. So they are forming some kind of protective layer on the top because of the presence of these carbide particles. And those protective layers are actually giving load bearing support, and they are preventing the nascent material down from getting worn out. So that is basically the tribolayer formation, which is inhibiting the nascent material to be worn out, and that is basically the tribolayer. You can see it is basically sintering of those wear debris that are formed basically in case of composite coatings. And why it is giving low friction is basically you have free carbon in the titanium carbide particles. Okay, that is the Raman analysis, and this free carbon is giving an easy shear because of the carbon, the graphitic carbon, which had a layered like structure. So it's giving easy shear. So that's why your friction is actually dropping to 0.3. So as soon as these layers form, because these layers are formed during the wear. So initial cycles where your tribolayers are not getting formed, you see high friction. And once you form these layers, the friction actually drops, and basically they form a layer on top, and that's why you basically have a smooth layer, and the friction basically you see a drop in coefficient of friction. That's what I was saying. Initially the friction is high because these layers are not yet formed, and once the layers are formed, the graphitic carbon is there, and then that graphitic carbon is providing easy shear. That's why your friction is actually coming down. So these tribolayers were even formed at higher loads also, but at higher loads the tribolayer was seen to be more continuous in nature, because initially at higher load you will get more wear debris and more continuous layers can be formed. Okay. So that's why we see a more continuous layer, and the friction actually dropped to a much lower value. Earlier it was 0.3, 0.33. When we increase the load, the tribolayer coverage was more uniform. So greater the coverage, the better the resistance, the lower the coefficient of friction. So that is one of the target. So we also looked at what is the chemical composition of the tribolayers. You see that apart from having this lubricating phenomena, the carbon particles also got fragmented and got embedded inside the tribal layer. So basically you see these small particles inside this tribal layer, they are small carbon particles which are present. So they give the load bearing support for the load which you are basically providing. So this is the deformed microstructure, and lastly we also measured the hardness of this tribal layer. So basically what we did, we cut the cross section of the bed track, okay, and then we did nano indentation. Okay, nano indentation we started. So this is the cross section of the bed track. Yeah, this is the cross section of the bed track, and then we started to do indents basically from unworn area to the worn surface, and then we plotted that hardness. This 0 corresponds to the top surface where you have tribal layer, and this way we are going actually as the surface. Okay, so initially at the near surface hardness of tribal layers where they are formed, since you have small carbide particles embedded inside these tribal layers, you see the near surface hardness is very high compared to titanium 64 where the hardness is low. Okay, the error bars are big because these tribal layers are very heterogeneous in nature. So that's why we are seeing big error bars. But if you look at the average, average hardness of the near surface of composites due to tribal layer formation is higher. So if the near surface is higher, it has more load bearing capacity and lower wear rates. Okay. We also did some TEM analysis, and we looked at how the grain structure actually looks like. And below the tribal layer, since you have less stress transfer, because the tribal layer basically has some load bearing capacity, you can see the coarse grain structures. Whereas the region where there is no tribal layer coverage, you see very fine grain structures. This can be seen by the continuous rings of the SAED pattern. So the higher the tribal layer coverage, the better it is for in terms of wear and in terms of friction. So last, the summary of wear mechanisms. In titanium 64, we have continuous debris formation, and these debris are basically flowing as the test progresses. That's why you are getting abrasive wear. In case of metal matrix composites, although initially some debris are getting formed, they are getting smeared and sintered around these carbide particles, forming protective layers, and that layer is basically giving you some kind of load support. And that's why your nascent coating is getting protected and the wear rate is basically coming down. So we also did tests at high temperatures, and even at high temperatures we found that composite coatings actually perform better due to glaze layer formation and all. So due to lack of time I will not discuss. And one thing we can observe is we had the chance to do some in situ tests. That is, you mount a microscope, use a transparent ball, okay, and measure how the friction is changing with respect to cycles. So I don't know if it will play. Yeah, it's a small video, but I don't know if it can be played. Okay. So basically, you can see that. Yeah. So you can see the ball is actually going. Okay. The friction is low at 0.3 because initially it has not started, just sliding on top, and as soon as you see the wear is starting to occur, the friction actually shoots up to 0.57, 0.6. Because initially it is between the ball and the sample, and once you start wearing, the transfer film formation occurs, and basically you see that the transfer film is getting formed on the counterface, and then that is actually controlling the coefficient of friction. So by using transparent ball, here we used alumina ball, transparent alumina ball, you can actually monitor the real time what exactly is contributing to the rise in friction. So that we could plot it due to different regimes. Okay, with different regimes we could see why the friction is going at which cycle number. So other composites which we already work in my research group in Canada include nickel tungsten carbide. My colleagues for mining equipment, alumina, aluminium, and copper MOS2. You see all are cold sprayed, and something you observe that there is a metallic matrix for every one, which is basically the deforming entity, and either you have basically the hard phase where you need some wear resistance, and if you need some solid lubrication, you put basically a solid lubricant like molybdenum disulfide, graphite, or anything what you can make. So lastly, conclusions. Abrasive flowing by the wear debris and scoring of the counterface led to high friction in titanium 64. In case of composite coatings, the presence of titanium carbide particles facilitated for tribal layer formation that resisted shear deformation, and facilitated for the easy shear of the counterface. Rival layer formation depends upon titanium carbide content and how easy can be formed. To best engineer titanium alloy and titanium carbide composite coatings, first you retain high amounts of titanium carbide, try to retain, and also you will maintain good cohesion and adhesion strength. And using nanomechanical testing, that is indentation, etc., you can assess the mechanical properties, the localized mechanical properties, and you can basically correlate to the friction and wear mechanisms what you are observing. So there are some publications, and I would like to thank my previous research group when I was working in Canada and all our funding sponsors. And thank you for your attention. If you have any questions, I have a question. Yes.
First of all, I want to say that my subject is not mathematics. My presentation was very nice.
Thank you.
Most of I attended previous FDP or the seminar. Each slides was the pool of information there. But your slides were very much clear,
Okay.
to the point, and exactly what you want to say, like a story.
Yeah.
You have completed your story. Thank you for that coming here. My question is that you have said you are making the coating and the heat transfer and the heating is down. You have coating, transfer is down. But you have said a data that 105 billion Canadian dollar to save. Is it correct or something?
Yes. That much they are spending basically to replace the worn out parts. Okay, so whatever parts are getting worn out due to friction and wear, okay, those parts have to be replaced. So the money that they are spending to replace these parts is equivalent to that amount. So for example, I have my cell phone. Suppose it breaks. Okay, I am breaking it every time, and I don't have a Gorilla Glass that is there on my phone. So every time I am investing 250 rupees to basically protect my screen. If I am putting a Gorilla Glass of 60 rupees, even it falls, my native mobile is safe. Only the glass is getting replaced, which is 60. So that means I am basically saying 190 rupees. So that is what equivalent I am saying there, that if you can reduce the loss due to friction and wear, okay, so my coating is like my Gorilla Glass. Cycle.
Also, I have to make questions on your side. That you have made a slide of data from 1990.
Yeah, that is not
2040 data.
Yes.
There several billion lines are there, horizontal lines are there. There you have made a line. Line was 2015.
Okay.
Horizontal line.
Yes.
4 or 5.
Yes. It's very initial.
Slide number 4 or 5.
Yes. I don't know how can I go ahead. Presentation. Yeah.
The data is from the 1990 and 2040.
Yes.
This data says you have saved by applying a coating, you save the money up to $105, and they are the horizontal line, they are the represent the heating etc. And the vertical line represent the 2015. Why it is the 2000?
So this report was published in US Times magazine in 2015. So that time the sustainability thing got picked up, and they tried to predict what is the energy that is being used and what is the source of energy. Suppose I have lightings, and you can always see in data that this much amount of energy is coming from thermal power plants. This much amount of energy we are using that for electricity, for example, is coming from hydropower. This much is from solar power. So that they try to normalize, and it is not a what I can say quantitative data. It's more like a qualitative data. So we are not going into the exact numbers. The thing I want to predict, the show is basically our energy consumption is rising day by day. Okay. For example, if you see now so many lights are being on, maybe after 10 years you will have more air conditioning. Now air conditioning is off, but in summer and all you use lot of air conditions. Okay, so the energy consumption day by day is increasing. and still lot of energy, although we are saying solar and all, still it comes from velocities. So if you don't heat your gas, okay, but the powder particles are not heated exactly, because if you see the diagram, the compressed gas goes and one more cycle goes and then gets heated, and then they both mix at the inlet of the nozzle and then you expand it.
Just increasing the velocity.
Yes, to get the increment in velocity. People still do at compressed gas also, they will get typically around 300 to 500 meters per second. And that is good to coat your low melting point material like tin, zinc, etc. But if you need nickel, okay, which are high in yield strength, titanium for example, you need a heated cast.
Sir, another thing.
Yes.
The ceramic material which is different and can it be deposited in the metallic surface? Because these are two.
Yes, you can deposit. Basically, you can deposit using plasma spray. You cannot do by cold spray, because as soon as ceramic impacts, it will undergo brittle fracture. So it will break, because ceramic powders, the way they are made, you have inherent porosity inside them due to manufacturing difficulties. So you will have inherent porosity and some cracks, and these will start to emerge out as soon as it impacts. Okay, so if you are using plasma, you are basically melting them. It's a molten particle, so you won't have brittle fracture there. Okay, so that way you can do.
Thank you, sir.
Thank you.
Good afternoon all. It is a very pleasure to be here. First of all, I would like to thank Mr. G to give me this opportunity to come back to my alma mater. I'm having lots of mixed feelings right now, so very happy to be present here and share some light in this topic which I've been working on. I'm assuming that most of you are from mechanical engineering department or other departments also.
Mostly mechanical.
Mostly mechanical. Okay, clear. So I will say something in the lines of microwave heating and its application. And I am Siddharth Tamar, as I was an alumni here back in 2008 and 12. So this is something which I have done in my PhD, which I will show you briefly. But overall, I would like to say or shed some light in this microwave heating and its application. So I have two groups in IIT Kharagpur which are working. One is in the area of material processing and welding. Okay, so laser does not show it there.
Yeah, that is the problem.
Because of its white.
We work in microwave processing, ultrasonic welding, laser welding, cold metal transfer welding, which is a GMW welding process. We also have GTFW, friction stir welding, and COMSOL is also coming soon. These are my students. And the other research group which I work with is in the area of wire arc additive manufacturing. As additive manufacturing is picking up in all the areas nowadays, so we are working with wire arc additive manufacturing, which is a way of manufacturing larger parts with the help of either CNC machines or robots in our case. So we have a Center for Excellence in Advanced Manufacturing Technology at IIT Kharagpur, and myself and Professor Surjakant Pal, we both together work with the area wire arc additive manufacturing. If you are interested, you are feel free to go in our website and check all the facilities available. So coming to today's content, I will be talking mostly introducing what is microwave heating, what is microwave hybrid heating, how we are using it in different applications like joining and other applications, and some simulations if time permit. So let's understand what is a microwave first. Microwave is basically an electromagnetic wave similar to our light waves, and it falls under all the electromagnetic spectrum. It has different frequencies ranging from 300 megahertz to 300 gigahertz. It might have a wavelength depending upon what frequency it is, from 1 meter to 1 millimeter. Generally, microwaves which we use for industrial purposes are in the range of having frequency 2.45 gigahertz. So since it is an electromagnetic wave, it acts simultaneously going at this frequency like 2.45 gigahertz. So that microwave is used in multiple applications nowadays commercially. For communication we know, and Bluetooth, Wi-Fi. For navigation also we use, even radar is a form of microwave. Medical sciences we use microwaves in order to, for cancer treatment, chemotherapy we use microwaves. We also use in industries for mineral processing. So if you want to reduce the hardness of a mineral before processing it, we also use it for drying the seeds in bulk. We also use it for drying your tea leaves and all these things. Drying is another way, and also cooking. So these are industrially used applications. Now, give you a theory of microwave. How does it heat up, and how do we use that energy, and in what way we do use it? There are multiple mechanisms of heating microwave. So firstly is the dipole loss, which is nothing but the heating which is happening with existing dipole will try to align itself with the fluctuating magnetic field, since it magnetic as well as your electric field, since it is fluctuating at a frequency of 2.45 gigahertz. There is friction in the water molecules, so it is creating heat. That is for dipole loss. Something is there which is known as conduction loss. This happens in elements where there is a lot of free electrons, like metals or even some ceramic. Electric field of the microwave will try to repel the electrons present, and it will try to send it towards the more deeply into the surface. When these electrons of the free electrons of the material travel, they create their own magnetic field. Okay? And this in turn also they create their own current, and the current will give their own magnetic field, and this magnetic field will again try to repel the electrons back. So there is a movement of electrons when the frequency is changing. So the movement of electrons is there, and since we have atom of electrons, and there is friction between the electrons and the atoms, so because of which heating takes place. This is the mechanism for conductive material. Then we have the hysteresis loss, which is a loss mechanism for materials which are magnetic in nature. So the other part of microwave, which is the electric field and the magnetic field. So this magnetic field will interact with some magnetic materials. Magnetic materials will have their own different domains, magnetic domains. Each domain will be oriented towards their own natural orientation. Whenever there is your magnetic field, so it will try to, this domain will try to align itself according to the magnetic field which is being imprinted to the surface. And so since the magnetic field is also changing at a frequency, so the magnetic domain will also try to align itself, because of which there is again friction between the small atoms, and thus there is heat. So another thing is about another mechanism is that generally there is sparking happen. Even in our home microwave, you see some label that warning, do not put any spoons or utensils. Spoons and utensils are basically bulk metals. So whenever we put bulk metal into a microwave oven, these the electrons which are there, they can tend to charge in the corners. Whenever they come to the corners, they whenever the cloud of electron is forming, basically there is some charge formation because we here and red is hot. Okay, so in conventional heating we have some heating elements which will heat something from the outside to the inside. So whenever you keep anything in a conventional furnace, it will be hotter in the outside than in the inside. However, in microwave, anything which you keep in the microwave, the microwave will try to penetrate and heat uniformly. The inner particles in any material will also be heated because of the heat of the surrounding particle. Is the inner is hotter than the outer for microwave. That's the reason why you put the burgers and everything. You know, outside it will be hot, but outside it may be cool. But now, how is this happening? This is basically happening because of the interaction of different materials with microwave. So microwave deals with materials because of electric and magnetic field. So electric field material properties like permittivity, dielectric constant, and magnetic field properties of material like permeability, magnetic loss. All this cater to if the permittivity is larger, the electric field will be dominant. If the permeability is large, the magnetic field will be dominant. So magnetic field and electric field will basically heat up a material depending upon what properties they have, each material. And so we have some loss standard which basically gives us the value that how much material will convert the heat, whichever has been inputted through the microwaves. And we have a terminology called skin depth. Skin depth is nothing but having a relation with the conductivity and the permeability. So there are different materials which distribute according to their interaction with microwave. Firstly, we call some materials which are transparent, where whenever we add microwave, it will pass through it. These are materials like alumina, zirconia, generally ceramics. Then we have bulk metals, which generally reflect the entire microwave whichever is there. That's why the microwave ovens walls are made of solid bulk metals. And we also have observers like charcoal, graphite. These materials fully absorb the microwave and convert the microwave energy to heat energy. Okay. So reflectors have very small skin depth. The skin depth which I was talking to you earlier. The reflectors have very small skin depth in the order of tens of microns, meaning that whatever microwave will be incident on metals, only from 1 to 10 micron the microwave will penetrate. Most all of it will be reflected back. That's what the skin depth means. And for transparent material, the skin depth will be very high, in the order of meters. So they will flow through and through. And in observers, it will be in the order of some centimeters. Basically, it will attenuate. The microwave whichever is incident, it will attenuate slowly converting into heat. Now we have something called microwave hybrid heating. That time we saw how microwave heating is anyways not heating something uniformly. Inside internal it is hotter, outside it is colder. In conventional, outside it is hotter, inside it is colder. But if we can use microwave hybrid heating, where we have some susceptors are nothing but observers. This observing material will directly absorb microwave whenever it is incident this will start heating from the periphery as your normal conduction, and internally with microwave it is heating. So we have uniform heating. So this is known as microwave hybrid heating. Okay. So we can get uniform heating, faster heating, and also some materials which are transparent materials, which I told you, in which microwave is not observed. This also can be heated up by microwave hybrid heating. Now, what happens is these transparent materials, if we increase the temperature of these transparent materials, they will start having changing the skin depth. So skin depth, which I told you, that is dependent upon the conductivity. The conductivity and permittivity. All this changes with temperature of a material. So with change in temperature of a material also, it starts becoming more absorbable for microwave because the skin depth is changing. That's how transparent materials are also heated up. Like ceramics can also be heated with microwave. Initial temperature. Because metals which are fully reflective, they can also be heated with microwave, provided we increase the temperature. Okay. So advantages of microwaves are multiple. You can do selective heating. So if you want to heat only some portions of any part, selective heating is there. That's what we use in our chemotherapy. Chemotherapy, we select some regions which needs to be heated by microwave so that we do not damage our internal organs. Volumetric heating we can do if we choose to heat some region which has direct compatibility with the microwave energy, that we can do. Very fast heating we can do here because we have heating at very high frequency. Heating is much faster, and because of which cost effectiveness comes into play. We can give defective structures. It's also environmental friendly if you come to do. So if the skin depth was around, let's say, this too we can modify by adding the. Now with that idea, what I have done earlier is we have this metal powders. We mix it in an epoxy resin. The susceptor will heat up, and then the powder particle which we added in as interlace, they will start heating up. Thus, it makes which I have used earlier to join your aluminum and magnesium alloys with epoxy, and the schematic you can see here. So aluminum and magnesium alloys generally used for lightweight application because of their low density and good strength to weight ratio. So this type of joint can also be done by microwave. And the interior that we have chosen is the zinc interior. So zinc, you can see here, has fully melted up and formed an interior in between the aluminum and the magnesium alloys. We have also used other interiors like active braze alloy. These are also very commercial braze alloy in the form of powder naturally, and which are also forming reaction zones, and we are getting very good joint with minimal of defects. So those were for low temperature alloys like aluminum, magnesium. High temperature alloys like stainless steel and copper, which has melting point above 1000. These also we can do microwave heating, and we can join these two. Here we have used copper itself as an interlayer. This copper is copper powder, and we have got the joint between stainless steel to copper. The application of these is anywhere between conductivity of copper requirement is there, and the anti-corrosive nature of stainless steel. So when we want to use both of these materials for each of their properties, we can use this joint. And what you can see here is when I'm using copper as an interlayer, you cannot see any joint between, because here anyways earlier there was metal powder in between. It was heated up and the joint was formed between copper and stainless steel. So you don't see any joint line because it is such a seamless process. It is a lot of diffusion is happening in microwave joint. So diffusion between the interlayer to the parent materials. In this case, copper being one of the parent material, and interlayer is also copper. There is a seamless joint between these two. We can also use other high melting like 1400 degrees Celsius is the nickel melting temperature. These also can be heated to that high extent, and we can form the joint between copper and stainless steel. The other application is of brazing. You already know the tungsten carbide tools which we use. These tools have some inserts. If you want to weld very, or if you want to machine very hard materials like high carbon steel or high strength steel, if you want to machine them, you cannot machine them with a diamond because there is obviously the graphitization of diamond. You have to braze them. You have to machine them with cubic boron nitride. Cubic boron nitride is also very hard, but it is an expensive material. You cannot make tool inserts fully of cubic boron nitride. So the cubic boron nitride is basically put at the tips of that machining these inserts, so that it can be brazed and we can do machining of this high hardness material. And the brazing, which is conventionally done by vacuum brazing, takes around 2 to 3 hours. Okay, the entire process. But we have done this in microwave. So we have taken tungsten carbide and then we have used the braze alloys in order to get the microwave brazing. So this is some results which we have got. Similar to earlier, we have a microwave oven in which, and these microwaves, by the way, are the normal. It is almost 3 to 4,000. The materials will cost some. The only thing is we have made a chamber and then we have put some argon gas so that the active braze oil does not oxidize. And we have again clamped the tungsten carbide with the cubic boron nitride, applied some braze oil and undergone microwave heat treatment or microwave heating to form these joints. So we see that the joints are having good metallurgical bonding between the parent materials and also good near net shaped manufactured parts. Earlier they used to do by powder metallurgy and conventional sintering, but nowadays we can also use microwave sintering. So we have powders, any type of powder. Here, as an example, there is copper and titanium, and then we mix the powders together to form these green samples, which are basically formed by some compression or some pressing, and then they can be either conventional sintered or micro sintered. What we have seen here, this is some results which we have done recently. So we use pure copper here, and if we have this green samples which are before sintering, we have compressed and made the small cylindrical samples, and then we undergo microwave heat treatment. This is a simple normal heating oven furnace, now which has been converted to furnace, and after sintering we can achieve this sintering of copper. This is at around 1000 degrees Celsius. Some years back I did some research in magnesium alloy composite formation by microwave heating, where these are some results from those times, where we can see that if you compare conventional sintering and microwave sintering, the conventional sintering has more corrosion, so corrosive resistance is checked here. So microwave sintering compacts have very good corrosion resistance. The reason for this is because we are getting very small grains in the microwave heat. You can see how with change in this different processes, even the hardness has improved. So we have to use composite or heat also ceramic particle also here. So for each ceramic particle, or what we have seen is, if you compare conventional sintering and microwave sintering, the hardness that we have reached by microwave sintering is much harder. So this is only because the metal particles are getting weaker, because of which we are getting grains which are smaller. So because of which the hardness is also higher. And obviously if we increase the heat percentage, because of more percentage of this ceramic, which is hard particles, they are getting higher particles. Microwave can also be used in casting process. This is not the research of our research. This is this is from IIT Roorkee. So we can also do microwave casting. So we have some refractory materials, and we have some, basically these are made of some susceptors. These susceptors heat up with microwave, and which is also made like a bonding basin. So the charge or the particles, metal particles, which will be added, will heat up because of heating of the in order to make some joints of your lab on chip, whatever thin channels or micro channels, whichever you make. We can also do those types of joining. As in most of these channels, micro channels, if you want to make them into chips or integrate them, we have to join them with some adhesives. So microwave curing is a very quick form of adhesive joining, where generally in curing temperature. So these are multiple applications of microwave heating, curing, sintering. So with that said, I would like to go towards the simulation aspects of it quickly within 5 minutes. So nowadays simulation is a thing where you do not want to waste any material to do experiments, and such that we can know the results of the experiment before actually doing the experiment. So microwave heating and is also can be done by simulation. This type of simulation we are doing in console multiphysics, but we can use abacus or ANSYS or any of those. But console is more friendly with microwave. So some basics of console. Console is a multiphysics software. This is a finite element method-based software where you can do 2D, 3D, or even 1D modeling problems. Multiple area of problems can be solved here, from fluid dynamics, from electric, from material science, thermal sciences, and many things. So what we have simulated and we have tried to compare here is the simulation of microwave heating and the experiment side of microwave heating. We took a cylindrical susceptors of different materials. This is silicon carbide. So and then we placed it in the microwave oven, we heated it up, and then we made this model in our console, and also tried to simulate the heating in console multiphysics. In multiphysics, we did multiple boundary conditions, which will basically simulate or help us to simulate the actual welding process, or in this case, actual heating process. So we use a boundary condition in order to show that as if it is a metallic walls where microwaves are reflected, which the impedance boundary condition. With the flux boundary condition, we give in the heat input, whatever you want to heat by the microwaves. We have port boundary conditions which help us to simulate how much microwave energy, what frequency is going into the oven. So here is some animation of with time. So I don't know if you can see here with passage of time how the heating of different types of cylindrical susceptors are happening. Silicon carbide, activated charcoal, graphite, all these are observable susceptors of microwave. So we can see the heating in terms of simulation heating. And if we see at certain time, let's say 300 seconds, we see that silicon carbide heats charcoal around 360 and graphite around 430. So all of these three are of same dimensions, but only time is same, but the material is different. So what we know is from this experiment and from the simulation, we know that graphite is the fastest heating in microwave, followed by activated charcoal and followed by silicon carbide. So that way you can tailor your hybrid heating. If you want to choose faster heating, you use graphite as your susceptible material. If you want to have slower heating, then you can use silicon carbide. So these are the graphs which actually says the heating rates of this different graphite, activated charcoal, and silicon carbide. With that, we also have simulated the joining methodology where we have joined up to the similar materials with the interlayer in between, and on top of it we have susceptor. And with the simulation we have understood that how the susceptor is hitting the highest, followed by the interlayer, and then the base materials are hitting not much. So here you can see the cross section temperature. So the susceptor is heating like around 1000 degrees Celsius. The interlayer particle is heating at around 900, and these are the base materials. This is the joint which we have simulated, and then we have also done some actual welding by microwave heating, and then compare the results. And the results are comparable. So thank you so much. I hope I was in time. This is my email ID, and my website can be gone through this link or through this QR code. As I am an alumni of this institute, I bear a lot of responsibility, and I would like to help any one of you who would like to do some welding or any type of other activities at IIT Kharagpur. So I will be happy to help you. Thank you so much for your attention. If you have any questions, you may please ask.
So I had one small question.
Yes, please.
Because this is the first time I'm seeing your talk. So what is the temperature maximum you can go in microwave?
Okay, so we can definitely go till 2000 degrees Celsius maximum, because in microwave there is something called thermal runaway. Thermal runaway is a term which we use when we cannot control the heating. As microwave heating is a property dependent phenomenon, the property of the material changes with temperature. So in some materials, the property changes so drastically after a critical temperature that we cannot control it. So then thermal runaway comes into play. So some materials will basically melt and evaporate because of thermal runaway, and we can control it by using susceptors and all this. So we can easily play between 600 to 1500 without thermal runaway. And before that, after 1500 degrees Celsius, controlling that is little bit tricky, but yes, we can reach 2000 also.
Sir,
Yes.
sir, how to control the temperature?
Yes.
For conventional way, we can control this, but microwave, how we can control? But even at 400 degree, 500 degrees.
Great. So if you are using a very simple microwave oven, like some studies which I have shown, you can control it by the temperature and your your power. So if you have larger amount of power, so wattage basically, then the heating will be higher. If you reduce the power, heating will be low. Microwave time, if you increase the time, heating will be more. If you reduce the time, heating will be. Frequency also can be changed. If you increase the frequency, heating will be higher. Reduce the frequency, heating will be lower. So multiple things can be controlled. That is for simple micro oven. If you have a oven which has a PID controller which senses the temperature and switches on and off, that is very easy for doing research. I'll be happy to answer the questions if you want to ask after this session also, and you can please email me also if you have any questions. Thank you so much for your attention. This crowd, but earlier I could see some familiar faces. I don't know if before I passed out, I don't know if all of you were there. I passed out at 2012, so I'm not remembering much faces. I think Professor, I am remembering you, but I'm not even able to match exactly which class you were. Sorry.
because you don't have galvanic corrosion. Suppose if you have some phase transformation and you are forming some intermetallic elements. Suppose you are spraying copper and you are spraying suppose in plasma or something, and you form on a titanium substrate. So you form copper titanium intermetallic. The corrosion rate of copper and this intermetallic is different. So there what happens is basically you form a galvanic corrosion. So one of the phase which has less if you have formation of films, in boundaries, you basically has higher passive film formation and it will basically protect your substructure. So since I have shown the splats where you have small grains, so localized sites where your passive film formation is more, so your protection is actually.
Actually, why I am asking this question, the nearby industries are mostly chemical in nature, and in the dock, you are referring to the application in the paper roll.
Yes.
So similar type of rolls are used. We support the conveyor while transporting the coal from one location to the other location.
Okay.
So they found that these rollers are being corroded and the life is reduced. So what solutions can you provide? So one major problem, wear and tear is definitely there, but what is typical in Haldia, that is the presence of corrosive environment.
Corrosion.
So that is how to protect industries. But Professor Bose along with some other faculty members is not present today due to some other reasons. So they had tried to coat them with some other materials. So I don't know whether to just for the as a prototype. So whether it will be possible for offering the long-term solution so that wear and tear and at the same time can protect from the corrosion. Okay, sir. Thank you. Please have a